Here we're going to talk about membrane potentials, and we learned in a different video that the membrane potential of a given cell is essentially the charge difference across the membrane, or we measure this as the charge inside the cell minus the charge outside of the cell. And so when I write this, I tend to draw little like lightning bolts, and I'll do something like this. Charge in minus charge out is equal to the membrane potential, which I abbreviate MP. Okay, so let's take a cell for a given moment, and let's use the ions that we've used in some previous videos, and sodium and potassium, and we're going to put a whole bunch of sodium on the outside of the cell here. So big letters, and we're going to put a bunch of it. And we'll put just a little bit on the inside of the cell, and we're going to put some sodium channels. And let's go ahead and do the same with potassium, but remember we got a high concentration of potassium on the inside of the cell. So some big letters. Quite a few of them. And then let's do a little bit of potassium on the outside of the cell, like so. And we'll also make the cell permeable to potassium by putting some channels on there. Okay, now let's use the same numbers from our previous video, and let's say that the equilibrium potential of sodium in this instance is equal to 90 millivolts, positive 90 millivolts. And let's say that the equilibrium potential of potassium is equal to negative 80 millivolts. Okay, so with that, let's say that our current membrane potential, and I'm going to write this over here, our current membrane potential is equal to 0 millivolts, no charge difference across the membrane. Okay, so with that, let's work through what direction will sodium want to flux. So sodium has a equilibrium potential of 90 millivolts. Current membrane potential is 0 millivolts. So it will want to bring that membrane potential up, right? So sodium will flux into the cell. So it will move into the cell to bring that membrane potential up closer to its 90 millivolts. At the same time, right, potassium is going to want to bring that membrane potential to negative 80 millivolts. So it has to decrease this membrane potential by taking a positive charge outside of the cell. So it will flux in this direction. So it will efflux or move out of the cell. So as these ions move, sodium will want to bring the membrane potential up to 90, and potassium will want to move to bring that membrane potential down to negative 80. So the question is, who wins? Where does the membrane potential sort of settle? Well, as these ions flux, right, they're going to reach a point where they are fluxing in such a way that the membrane potential will eventually fall in between them. So we will say like final membrane potential as the ions move is going to be equal to somewhere in the middle of those two things. So let's say that it is positive 5 millivolts, right? So a happy medium between our 90 and our negative 80. So the membrane potential, so the final membrane potential would be about 5 millivolts, okay? But what happens if I give sodium a little bit more of an edge to move faster, more readily, easier, right? How do we do that? How do we increase that transport maximum of that ion? Well, we can add in more channels, or we can open more channels. We can increase the permeability of the cell to sodium. And as I increase the permeability of the cell to sodium, how is that going to impact my final membrane potential? So if I increase permeability of the cell to sodium, right, the membrane potential becomes closer to sodium's equilibrium potential. So instead of it being positive 5 millivolts, maybe it becomes positive 60 millivolts. Right? And if we were to increase the permeability even more, it might move to positive 70 millivolts, might move to positive 80 millivolts, right? And so the final membrane potential is going to be dictated on a couple different things, right? So if we think about the membrane potential, right, the membrane potential is that charge difference across the cell membrane, and that cell charge is going to be dictated by the ions that are going to be present. So if we think about the membrane potential of a given cell, right, our membrane potential of our example cell that we just used was dictated on the equilibrium potential of the sodium, and it was dependent on the equilibrium potential of potassium, right? But we also have to remember that the membrane potential can be dictated by the permeability of the cell to a given ion. So remember that we could calculate the equilibrium potential of a given ion using the Nernst equation, right? And the Nernst equation, if we sort of rewrite this up here, remember our Nernst equation was RT Z sub F times the natural log of the concentration of the ion in over the concentration of the ion out, like so. And the Nernst equation told us the equilibrium potential of a given ion. Well, we know that the membrane potential is a derivative of the equilibrium potentials of all of the ions that might be present. So if we did a little bit of math, right, we can pull out our constants, RT over F, and then we can multiply that by the natural log of the concentration of ion A over the concentration of ion A, right? So this is in, out. But one of the things that we have to keep in mind is the permeability of that cell to that given ion. And we have to keep in mind what ions are present. B, what about ion C? And so on and so forth, right? And so this is something known as the Goldman-Hodgkins-Katz equation, or what we refer to as the GHK equation. And that GHK equation will tell us if we know what all ions are present, and we know the equilibrium potential of each individual ion, right? We can use the equilibrium potential of each ion plus the permeability of the cell to each one of those ions. We can ultimately determine what is the active charge difference across that cell membrane, or what is the current membrane potential.